Hey everyone, welcome back. In this video, we wanna see a solution for problem 1564, put boxes into warehouse 1. In this problem, like the one that you can see on the right, we are given a warehouse and we wanna put boxes into this warehouse, and the task is to maximize number of boxes that we can fit into this warehouse. So there are some limitations such that each warehouse has a length. For example, this warehouse has a length of 5. We have 5 rooms, and each room has a height. So if we split it like that, and the boxes that we want to put into this warehouse also has some heights, but the thing is we cannot put boxes on top of each other. So for example, we cannot bring this one and put it on top of, stack them basically. So we can only put them back to back, moving them, and then the next one. So for example, as you can see, for given this set of boxes, this is the maximum we can put, at maximum 3 boxes into this warehouse. So basically we can move the green one first all the way to the right, and then choose the blue one, and then since blue passes this height, we cannot move the yellow one and the red one, so because both of them will be stuck at index 0. So but the blue one we can move it all the way to here and then put it here, and finally we can choose either red or yellow and then put them here, and since we have no room left at the warehouse, we can put it there. So there are two concepts that we can discuss. First of all, let's sort all the boxes that we want to put in sorted, so from smaller to the larger. If we have 2 boxes, and box 1 and box 2, and we know that the second box, so this is 1 and 2, h2, let's say in this example, is greater than h1. Let's say for each box we want to see what is the maximum index in warehouse that we can push the box into. In this example, we can push green all the way to the maximum index 4. This is the index that we are discussing here. If we find an index for box 1 and name it I, can we put or push box 2 to any index greater than I? The answer is no, because if this is the index that we put the maximum, and this was a limitation, either the rest of the rooms were full or blocked, or at the height of the next available were smaller or equal to the height of box 1, and since we know the height of this new box is smaller than the previous box, I is still the maximum index that we can put the height box 2. And if we already put box 1 into an index I, so index for this larger one would be anything from 0 to I minus 1. So we remove that. In this example again, whenever we put, this is the smaller box, we put it here. And for the next one, we know that we have put the green box into index 4. So for all of them left, since all of them are larger in height, at the maximum index we can push them is 3. So for that, let's jump into the development for the anything that we discussed so far. So first of all, let's sort boxes by height. So boxes equal sorted boxes. And now, starting from 0, I is the first box that we want to see. Or let's box index, let's name it box index from 0. We are starting from 0. And then we also have a top, or the top index. The top equals the length of warehouse minus 1. So the last thing, initially, we know that since the index of the last available room is 4 in this case, and we want to see if we are starting from a smaller one, can we put go there and put it there. So while top is greater than or equal to 0 because we are starting from the last room, and then eventually we are shifting left. And as soon as we jump out of the warehouse, so the top index, which is here, is -1. So that means there's no room left in the warehouse. So and bi is also less than the length of the boxes. So that means we are still have some boxes left to put into the warehouse. Other than that, we have already put all boxes, so we can break the program and jump out. So the box that we want to put in is boxes the bi. So this is the box that we want to put. So for each box, for a given box, now let's ignore all of them, and then let's focus on one box, which is the bi that we want to put into this warehouse. What is the conditions? So we know that this is the top. For each, we should check that if all of the previous indices are the height of the rooms for all previous indices, including the current one, is at least 1, or all of them are in height are greater than or equal to the box, the height of the box that we want to put forward. So if any of the height of the rooms around here was smaller, so if didn't have this part, we could still put this all to the right, but after that we couldn't fit the blue one. So it is, in terms of performance, it is expensive, since we know that the warehouse could have lots of rooms. If we want to, for each box, we start from I and then compute the height of the all rooms from index I to top, to see what is the minimum. Are all of them at least 1 or not? So it's the complexity of that. For each box, we should iterate in on if n is the number of rooms in warehouses, and it is computationally expensive. So for that, we can use a dynamic programming to store the minimum height for each index. So what I want to build is another array, and we build it using dynamic programming or recursively. And for each index in this min list, or min height, let's say, or min room, each index indicates the minimum height of all rooms on the left to the current one. So index I is equal to the so let's say we have a min room equals initially warehouses 0. So each index in this min room, or min room I, equals to the minimum of warehouse j for j in range I. So we can either build this in ON2, but instead, if we use dynamic programming, we can build this in ON instead of n squared by so for each W, the capacity, or for each capacity in warehouse, we already put warehouse 0 into the array in warehouse 1 onwards. So the min room, the depend, what is the minimum of the new room? So if we only keep track of the minimum height from anything on the left, so we should only compare the minimum of the current capacity with the last element in the min room. So this is the minimum of anything from 0 to I minus 1, and we'll compare it with the current warehouse, and then put it on the top of the min room. So the lengths of min room and the lengths of warehouses are the same, and the difference is that instead of representing the height of each room like it is given in warehouse, min room represents the minimum of all the minimum height of all rooms in the warehouse starting from index 0 to I. So we built this in ON. This part is now in ON instead of ON squared. We also sorted them in ON log n here. Or for if let's make it different, if we have n boxes and we have m warehouses, so we are building this in OM and first sorting boxes in ON log n. And then after that, again, we want to see while top is greater than or equal to 0 and the box is greater than the greater than the mean room of top. So for a given index, while the box is larger, in this example, whenever, let's say we already put these two and we are considering it for red, so we are now currently at this index, while it is the mean room for that index is smaller than the box, so we are now moving to the left, trying the next one, until we, as soon as we find a room that its capacity is equal or larger than the current box that we want to put into the warehouse, we just put it date, assign it, and then move to the next box that we want. So for that, and also we want to make sure that we never put anything beyond the warehouses. So this is the condition that we never check in, until index 0. So top minus equal to 0. That means we are rejecting the room and then trying the next one, until eventually either we have no room left or we find a warehouse room that we can feed the current box, incoming box into. So here, first check if top greater than or equal to 0. That means that's a good sign. We already found a room, so we can increase the box index by 1. So we increase it by 1. And also, since we already assigned it, we can no longer put anything after that, because whenever we put a box, it is blocking the way. So anything left out of the warehouse at maximum can reach to the next available room on the left of the current room that we are putting the box in. So with that, I'm also decreasing top. So whenever it's over, we know how to count number of boxes that we have put in already. With that, we can also use the box index that we are using. So starting from 0, whenever we find a room, so we are increasing that by 1. So this box index itself also representing number of boxes that we have put into the warehouse already. So with that, I can just return the box index and try that. And so for C in, I forgot in, top minus equal 1. And there it is. So let me submit that. So it's faster than 90% of the solutions accepted for this problem. And we use dynamic programming to compute this in OM in list and sort the boxes in O and log n first. So this one, since we can only visit each room, we are visiting each room in the warehouse once at maximum, and also each box at most once. So for that, the complexity of this part is also O m plus n. The time complexity of this part, as we discussed, is O, this is the m and n, so this is in O m, and O n log n. So the total time complexity for this problem is O n log n plus O m plus O m plus n. So we can ignore this part since this one is larger. So it would be O n plus n plus O n log n, the time complexity. And the memory complexity for this problem would be, since we are the boxes is given, so we are not allocating extra memory to fit the boxes in the memory. We are only initializing or creating memory of size m to store the minimum that we built it recursively using the DP for that. So we are allocating an extra OM memory into the in this problem. So that was everything for the solution and the complexity of this solution as well. Hope you enjoyed it.